So section 4.3, we're going to multiply and divide rational expressions today. And we talked a little bit about rational expressions on the last lesson, and we talked about simplifying rational expressions and doing that type of thing. I'm just going to kind of go over just a few examples to make sure we're okay with simplifying rational expressions here first. Give you a little bit more of a formal definition and really give you too formal of a definition last time. So I'll give you a little bit more formal of a definition today. And then we're going to look, after we do some simplifying questions, we're going to go ahead and look at both multiplying and dividing rational expressions. So essentially what it does become is multiplying fractions. But now they're going to be rational expressions instead. So by definition, a rational expression is the quotient of two polynomials. So x squared over x squared minus 9. It's two different polynomials. Yesterday we did things like 5 over x. It's two polynomials. The part we didn't talk too much about yesterday was the domain. The domain, remember, is that x value, how far it can go left and right on the graph. In the domain of a rational expression is all real numbers except those for which the denominator is equal to 0. So if we look at x squared over x minus 9, that's an example of an irrational expression. Now, because if we want to find the denominator, because the denominator can equal 0 if x is equal to 3 or negative 3, then we say the domain of this is all real numbers except for 3 and negative 3. And how do we know that it's 3 or negative 3? Well, to find the domain, it's going to be all real numbers except for when the domain is equal to 0. So really all we're doing is saying, all right, x, take the denominator and set it equal to 0 and solve. Oops, that should be a 0. Set the denominator equal to 0 and solve. So we've got x squared minus 9 equals 0. So x squared equals 9. So x is equal to plus or minus 3. So that's where that plus or minus 3 comes. And it's important that we know where that domain is, because in this case, this graph, doesn't exist at those two domains where x is equal to 3 and where x is equal to negative 3. So whatever this graph might look like, we've got this vertical line at 3 and we've got this vertical line at negative 3. We've kind of got these vertical lines where x is equal to negative 3 and x is equal to 3, where this graph doesn't touch. Okay, so again, we're not going to worry about too much of the graphing of this, but you do need to know that this graph very well may well, instead of guessing what it looks like, let's go ahead and see what it looks like on Desmos. And again, we're not going to worry about the graphing piece of this too much, but let's just kind of see what it looks like. So we had x, I forgot what we had. Of course, I did. We had x squared over x minus 9, so x squared divided by, and we'll put it inside parentheses, x squared minus 9, is that what it was? X squared minus 9? Well, we should probably get rid of that. Let's put it down there instead. Let's go x squared minus 9. And so this is what that graph looks like. Yesterday we talked about a little bit about that was 1 over x. And things happen now, it's not 1 over x anymore, it's x squared. So some little bit things change, but what you'll notice is that if I zoom in on this a little bit, our line for 3, our graph of, so if I plug in there x is equal to 3, there's a line for x is equal to 3, and here's a line for x is equal to negative 3. Those are our domains, and you'll notice that the graph continues on till it gets close to that, but it never intersects with it. So that's kind of that asymptote line, that vertical asymptote line. And then the graph starts to exist again after we get past 3, from negative 3 to 3, and then it stops. It goes down, and then again it exists on the other side. So this is what this graph looks like. Now there's both vertical asymptotes and horizontal asymptotes within this, but this is what essentially this graph is going to look like. And again, those asymptote lines are when that denominator is equal to 0, and obviously we know that we can't divide by 0. So that's kind of what that graph is going to look like. So let's take a look at the example here where we've got x cubed minus 5x squared minus 24x, and we're going to divide that by x cubed plus x squared minus 72x. And we're going to find, we're going to write its equivalent expression. So we're going to simplify it, just like we did yesterday. So we're going to have to factor first, and I don't have a whole lot of room here, but we'll do the best we can. So the first thing I'm going to do is, in this top one, is I'm going to factor out an x. And that leaves me with x squared minus 5x minus 24. And then I can probably factor that in there. My guess is it's going to be x minus 8 and x plus 3. So that's our numerator. That's a nice 3. Or x plus 3. So that's going to be our numerator factored. And I'm just going to put a little bit of a circle around it so I know where it's at. Change colors here for the denominator. I can take out an x. And then that leaves me with x squared plus x minus 72. So that's x times x plus 9 and x minus 8. So when we look at ones that are the same, that's divisions is going to give us 1. These are the same. Those are going to give us divisions of 1. So the simplified form of this is on the numerator. I've got x plus 3. And in the denominator, I've got x plus 9. So that's the simplified form of this. Well, now when you're talking about the domain of this, if you're asked what the domain of this is, the domain of this is actually when the denominator could be 0. And it's not when its equivalent to 1 could equal 0. So what we have to do when we're trying to find the domain of this one is, see if I can add a page in here. What we actually have to do when we're trying to find the domain of this is we have to kind of take that whole numerator, which we had x and we had x plus 9, or the denominator, and we had x minus 8. That was our denominator. When we're trying to find the domain for this, it's all real numbers except for when this is equal to 0. So you have to take that before you kind of reduce and figure out which pieces of this make it 0. So that's 0, that's negative 9, and that's 8. So we've got 3 different spots. We have 3 different really asymptote lines on this. So our domain for this one would be all reals, except x equal to 0, x equal to negative 9, and x is equal to 8. Because if x is any of those values, then that makes that denominator 0. So that's what we're talking about when we're talking about domain and range, is when that denominator can be 0. And again, you have to think about it from the initial problem before you've done any reducing. Okay, so let's look at another example or two. So it says, what is the simplified form of the rational expression? What is the domain for which the identity between the two expressions is valid? Okay, so we're going to go ahead and factor the top one. So if we factor the top one, I notice the 4 is a perfect square and the x squared is a perfect square. So we've got that difference of squares. Square root of 4 is 2. Square root of x squared is x. So that's 2 minus x and 2 plus x. On the bottom, factor tree. If you have to use the factor tree, negative 10 and 3. So 5 and negative 2. So then that becomes x plus 5 and x minus 2. So now you ask the question, are any of these equivalent to each other? Well, you've got a 2 minus x and you've got an x minus 2. Are those two things the same thing? And the answer to that is no, they're not. But is there something I could multiply that top thing by that would make it the same? And the answer to that is yes. I could multiply it by a negative. If I multiply this top by a negative, or at least this top one by a negative, this 2 minus x would then become negative 2 plus x. And then I still have that 2 plus x, because I only have to distribute this negative into one of them because of the multiplication. Then x plus 5, x minus 2. Now these two things are equivalent to each other. So your solution to this is the negative of 2 plus x over x plus 5. That's the simplified form of this. Now we have to figure out what's the domain. When we're listing the domain, we're always going to put it's all reals. So signification for all reals is you can just put that symbol right there. And then we look at our factored form. So that factored form is negative 5 and 2, so it's all reals except x equal to negative 5 and x is equal to 2. So there are our solutions for that. So that one's a little bit tricky, given the fact that you have to multiply that top one by a negative. Just kind of something, if you see something that are they're opposites of each other, just multiply one of them by a negative and you're good to go. And you could have moved that negative either direction, it wouldn't have mattered. Okay. So why don't you go ahead and do part A. Simplify the expression and then figure out what the domain is. I'll put a filler in here, about 30-second filler in here, and then the answer will be there when you're ready to go. Okay, so there's your solution. Solution's down here kind of in the corner, a little bit hard to see. So finalize it, you get x plus 1 over x minus 3. And then our domain is all reals, except for x cannot equal 0, negative 1, and 3. So there's kind of what we did yesterday with adding in, finding the domain and the range. It's late, it's like almost 6 o'clock and I'm still doing lessons. And I'm losing my voice, coffee break. Today then, what we want to concentrate on is we want to concentrate on multiplying rational expressions and how we go about multiplying rational expressions. Now, rational expressions are fancy fractions. So when you multiply fractions, say that I had something like 2/3 times 4/6. There's a couple different ways you could do it. One of the easier ways to do it is and what you do anytime you multiply fractions is you take the top times the top and the bottom times the bottom. So you can go 2 times 4, which is 8, 3 times 6, which is 18, and you can have 8 over 18, and then do your reducing now. So 2 goes into it, so 4/9. So the reduced form of that fraction is 4/9. That's one way to do it, and you can always do things that way. And sometimes that's the easiest way to do it, especially when you're looking at kind of the one that we're going to work on here in just a second. Anytime, we'll talk about it in a second. The other way that you could take this 2/3 times 4/6 is you could do some of the reducing beforehand. As long as something's in the numerator and something's in the denominator, you could reduce it. So I could reduce this 2 with this 6 and say that 2 goes into itself once and 2 goes into 6 3 times. So now I've got 1/3 times 4/3, which is 4/9. You can do them across things. And again, you're multiplying, so it's top times top and bottom times bottom. The other thing that you could do, and this is just kind of all fraction stuff, and it worked well in this one, and it doesn't always work there. I could have reduced the 4/6. They have a common factor of 2, so that becomes a 2, that becomes a 3. You still get 4/9 as your solution. So it doesn't matter as long as if it's in the numerator and then in the denominator, you can kind of cancel them out, divide them out, as the guy said yesterday. So if we're trying to find the product of this rational expression, essentially we've got a monomial on the top in our numerators, and we've got in our denominators as well. So anytime I have something like this that's not a polynomial, I just multiply it out and then I do the reducing later. It's just, in my mind, it's just easier. It becomes less crossing out. So I'm going to take 2 times 3. So I'm going to go top times the top. 2 times 3 is 6. X times x squared is x cubed. Y. Bottom times the bottom, I've got 4y. And then z times z is z squared. Now I can reduce. 4 and 6 reduces to 3 and 2. I don't have any x's in my denominator. My y's, I've got one y on top and one y on the bottom, so those are going to go away. Oops, I said they're going to go away, but I wrote it down. And then we've got that z squared in the denominator. So that's our solution. Certainly one way to do it. And anytime I've got 2 monomials, I just find it easier to do that way. Doesn't mean that that's how you have to do it. If you wanted to do the reducing prior to, there's certainly nothing that says you can't do that. If I want to cross out, well, I've got a y here and I've got a y here. If I want to cross those out, I can go ahead and do that. If I want to cross this 2 and this 4 out and make that a 2, I can do that. And now I've got 3x cubed over 2z squared. Same answer I had before, just a different way to do it. And it's up to you which way you want to do it. That's your call. Anytime you have monomials and monomials, either way works. Where doing it that way doesn't work very well is when you have something like this. You're not going to want to multiply all of this out and then factor it and then do that type of thing when you're looking at multiplying a bunch of monomials and binomials and trinomials together. This is where your factoring is going to come into play. And you want to factor every single thing that can be factored and rewrite everything that can be rewritten. So I'm going to go through this piece by piece and factor every single piece that can be fixed. So I'm going to put this in simplified form. So I look at the 5x, and the 5x, nothing can be factored out of that, so that's just going to be 5x. X plus 3, nothing can really be factored there, so I'm just going to put the x plus 3 times. Now I'm guessing that x squared plus x minus 6 can be factored using the x method. Okay, I'm just going to guess and check it because we should be getting, at least with this kind, it's not so bad. So x plus 3, x minus 2. That looks like that's right. That gives me negative 6. That works. Same thing with the bottom. I'm going to factor it. It's x plus 1 and x plus 1. And I'm also going to do this to the last one. 2 terms, look for a GCF. It's got a GCF of x. So I'm going to take an x out of that. That leaves me with x plus 1. The bottom, 2 terms, look for a GCF. It's got a GCF of 5. That leaves me with x minus 2. Okay, and double check my factoring. Make sure I'm okay. Looks like I'm okay. Now I look for terms that are in the numerator that are also in the denominator. I've got an x plus 3 down here in this denominator and an x plus 3, so those two can divide each other out or cancel each other out. I've got an x minus 2 here and an x minus 2 here, so those can cancel each other out. I've got 2 x plus 1s and an x plus 1, so I can only cancel out one of them. Okay, so I'm going to cancel those out. And then I also have a 5 here and a 5 there. So those can cancel each other out. So on the top, I'm left with x times x, which is x squared. And on the bottom, all I have left is x plus 1. That's my solution. Now it's asking you just to simplify it. You don't need to state the domains right now. So we wouldn't have to worry about the domains being all reals except for -3, -1, and 2. You're just going to simplify these today. You're not necessarily going to find the domains, at least when you're multiplying them. So I find this much easier to do than multiplying it out and then try to factor that whole mess. Again, remember that anything's in the numerator can be canceled out with anything that's in the denominator. Okay, so let's look at another one. And we'll do this one together. So we're going to find the simplest form of each product. And this one, they want us to give the domain. Okay, well, if they want us to give the domain, I guess then that's what we're going to do. We're going to give the domain. So I'm going to go ahead then and factor x squared minus 16, difference of squares. So that's going to be x, square root of x squared is x, so x minus 4, x plus 4. The bottom. Now here's what I'm looking at when I see this 9 minus x. I know everything else I'm going to have is going to be x something and probably an x positive. So I'm actually going to factor out a -1 out of this because it's backwards. And then that would give me -9 plus x, which is x plus 9. So it makes my life a little bit easier if I do this right away because you're going to end up having to do it anyway. So I'm just going to do it at that step. Times, now we're going to factor this, so a little bit more difficult, 9 and 10. So this would be x plus 10, x minus 9. Oops, I'm sorry, I made a mistake back here, didn't I? This should have been, my apologies, back here. That right there should be x minus 9. Sorry about that. Again, my apologies. But we can talk about how did I notice it. This should have been x minus 9. How did I notice it? I noticed this was x minus 9 over here. So because that was x minus 9, I figured I had to have one on the bottom. So nice way to double check. Sorry about that. On the bottom, so x plus 10, x plus 4. Right, now I'm going to need all of that, but I'm going to go ahead and take the like ones. So I've got x plus 4 and x plus 4. I've got x minus 9 and x minus 9, x plus 10, x plus 10. So I'm left with a solution to this one. On the top is x minus 4, all of that over -1. And you can leave it like that, and there's nothing wrong with that. If you wanted to put -x plus 4, you could put that. It's the same thing. Okay, sorry about that. My battery's running low on my phone. So there we're sitting with that. Now, the domain and the range. For the domain and the range, you need to go back to this part right here. So what makes that 0? 9. What makes that 0? -10. What makes this 0? -4. So it's all reals, but x cannot equal 9, -10, and -4. So when you divide fractions, you multiply by the reciprocal. So when you divide rational expressions, that's what you're going to do. You're going to change it to a multiplication question and multiply by the reciprocal. So really what this question comes, and I'm looking at 1 over x squared plus 9x divided by 6 minus x over 3x squared minus 18x. We can rewrite this, and you should rewrite this as 1, let's get a pen here instead, 1 over x squared plus 9. And if you wanted to factor that right away, you could have. But we're going to change the division to multiplication, and then this is going to become 3x squared minus 18x over 6 minus x. So you multiply by the reciprocal. So we flipped that second part. Now we can go ahead and do the factoring pieces that we need to do. So this first one, obviously 1 doesn't have a factor. This can become x times x plus 9. This, take out a 3x, and that becomes x minus 6. Yep. X minus 6. And on the bottom, I've got this 6 minus x. Well, remember, I can just switch this around. If I take out a minus, that becomes x minus 6. So that's what I'm going to do. Now I can go ahead and do my reducing. I've got x minus 6 there and x minus 6 there. I've got an x here and an x there. So on the top, I'm left with 3. And on the bottom, I'm left with negative x plus 9. That's the solution. The domain, I have to go back to this part right here, and it is this part right here because it's a multiplication problem now. And what's going to make that denominator 0? Okay, so it's going to be 0, all reals except for 0, 9, and 6. So there's our solution for this one. Okay, let's go down to part B. This time I'm just going to factor them right away. So 2x squared minus 12x over x plus 5 divided by that. So I'm going to factor the first one so I can take out a 2x. If I take a 2x out, that leaves me with x minus 6 over x plus 5 times, I got to flip this, so x plus 5 over x minus 6. Cancel, 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 cancel. Solution to this is 2x, all reals. X cannot be negative 5 and 6. And you're done. So that's multiplying and dividing rational expressions. Remember, when you're multiplying and dividing rational expressions, that it's top times the top, bottom times the bottom. Do your reducing with your fractions within there, and then go from there. Next lesson will be on adding and subtracting. We're going to do this over a couple different days. We're going to start with just monomials, adding and subtracting rational expressions of just like monomials. So 3x squared divided by y squared plus 3y squared divided by x squared, or plus, I mean. And then we'll work on adding and subtracting polynomials as far as things go. And there's my dog, so that must mean it's time to be done. So there is lesson 6-4. Assignment on this is the PDF that's there. Make sure you follow directions on the assignment as to which ones you need to do.